this video, I'd like to talk about ionic bonding and metallic bonding as covered in chapter 6.3 and 6.4 in your textbook. Let's begin with ionic bonding. What is an ionic compound? Well, as the name implies, it is a compound made up of cations and anions. What kinds of elements make up ionic compounds? Well, what kinds of elements form ions? Metals and nonmetallic elements. How are ionic compounds formed? Well, we learned in the last unit that the metal will lose one or more electrons to form a cation, and the nonmetal will gain one or more electrons to become an anion. And once you've got cations and anions, you've got an ionic compound, which is held together by ionic bonding. What is the formula of an ionic compound? We haven't really talked about chemical formulas much yet, but we will very soon. But for now, I can tell you that the formula of an ionic compound is a representation of the composition of the compound that tells you which elements make up the compound and their relative amounts expressed as the simplest integer ratio. And in the formula, the cation is always shown first. So the question is, how are we going to determine the relative number of cations and anions in the ionic compound? Well, that's going to depend upon something very important, which is called the principle of electrical neutrality. An ionic compound is overall electrically neutral. It has neither a positive nor negative charge, so that must mean that the positive and negative charges are exactly balanced. So specifically, the principle of electrical neutrality says that the total positive charge from all of the cations must be equal in magnitude to the total negative charge from all of the anions. That way, the charges balance and the compound is neutral overall. So let's see how we use this principle to actually predict the formulas of specific ionic compounds. It's very straightforward. So in each of these examples, I give you a pair of elements. One is a metal, one is a nonmetallic element, and we're going to predict the formulas of the ionic compounds they form. The first question we ask ourselves is, what is the symbol of the ion that each element forms? Well, we learned in the previous unit that metals lose all of their valence electrons to form cations that have the configuration of the previous noble gas. Nonmetallic elements gain enough electrons to completely fill their valence shell, acquiring the configuration of the next noble gas. And the charge on the ion is equal to the number of electrons lost or gained. So let's take the first example. We know oxygen needs to gain 2 electrons to fill its valence shell. The symbol of the oxygen anion is O2-. Magnesium needs to lose 2 electrons to empty its valence shell. It forms a cation with a charge of 2+. Now, because the charges are equal in magnitude, but opposite in sign, that means I need an equal number of magnesium 2+ cations and oxygen 2- anions for the overall charge to add up to 0. So a 1-to-1 ratio is sufficient. So I will write the formula as MgO, indicating a 1-to-1 ratio of magnesium cation and oxygen anion. Okay? And again, by convention, the cation always goes first. Barium needs to lose 2 electrons to empty its valence shell. It forms a cation with a 2+ charge. Fluorine needs to gain 1 electron. It forms an anion with a single negative charge. But now, in order for the overall compound to be electrically neutral, that is, for the charges to add up to 0, I need 2 fluorine anions for every barium cation, and I write the formula as BaF2. Nitrogen gains 3 electrons to form an anion with the configuration of the next noble gas. Potassium loses 1 electron to empty its valence shell. Now to balance charges, I need 3 potassium cations for every nitrogen anion, and I write the corresponding formula as K3N. Aluminum has 3 valence electrons. It loses them to form a cation with a 3+ charge. Sulfur needs 2 electrons to fill its valence shell. It forms an anion with a 2 negative charge. If I have a 3 positive charge on my cation and a 2 negative charge on my anion, I have to ask myself, what's the least common multiple of 3 and 2? Well, it's obviously 6. So my total positive charge must be 6+, my total negative charge must be 6-. In order to do that, I need 2 aluminum cations for a total positive charge of 6+, and I need 3 sulfur anions for a total negative charge of 6-. Writing this as the simplest integer ratio with subscripts, I will write the formula Al2S3. Now, that leads to the concept of the formula unit. What is a formula unit of an ionic compound? The definition of a formula unit is the simplest collection of cations and anions that make up the formula of an ionic compound. So, what I expect you to be able to answer is how many ions are present in one formula unit of the ionic compounds in the previous problem. For MgO, one formula unit of magnesium oxide is 1 magnesium 2+ cation and 1 oxygen 2- anion. So that has 2 ions per formula unit. In BAF2, I've got 1 barium cation and 2 fluorine anions. That's a total of 3 ions in the formula unit. K3N has 3 potassium cations and 1 nitrogen anion, so that's a total of 4 ions in the formula unit. And finally, for Al2S3, I've got 2 aluminum cations and 3 sulfur anions, so that's a total of 5 ions in one formula unit. So what do ionic compounds look like on the submicroscopic level? Well, the ions lower their potential energy by forming what is called a crystal lattice, and that's a very important term. A crystal lattice is an orderly, 3-dimensional array extending in all dimensions with balanced positive and negative charges. And here is a depiction, 2 depictions actually, of the crystal lattice of sodium chloride. In each of these 2 depictions, the purple sphere represents the sodium cation with a single positive charge. The green sphere represents the chlorine anion with a single negative charge. On the left, structure A is sometimes called the ball and stick model. It shows the ions as spheres, and the red sticks represent the electrostatic attraction among adjacent ions. B is called a space-filling model because it shows the ions with their electron clouds, and you can see that they're very tightly packed together. The idea is, in the crystal lattice, you get oppositely charged ions as close to each other as possible because they're electrostatically attracting each other, but you keep similarly charged ions as far apart from each other as possible in order to minimize repulsion. The result is the lowest possible potential energy. Now, this is simply one type of crystal lattice, and there are many other types, and on this slide I show you some other examples. The previous slide showed the sodium chloride lattice. This is cubic body-centered, cubic face-centered, and hexagonal. You don't need to know any of these. In fact, all I want you to know is what a crystal lattice is and that there are a variety of different types of crystal lattices. Now, what are some properties of ionic compounds? They are all solid at room temperature. No ionic compounds exist as liquids at room temperature, and they have very high melting points. That's because ionic bonding is actually quite strong. It takes a lot of energy to separate the cations and anions. Okay? In my laboratory, I have tried to melt sodium chloride over a Bunsen burner flame. I cannot do it. The melting point of sodium chloride is a couple of thousand degrees Celsius. They are very hard and brittle, and I'll show you in a minute why that is. They are non-conductors of electricity because there are no charged particles that are free to flow through the solid. So here's a diagram that illustrates why ionic compounds are brittle. On the left, we see an ionic compound with alternating cations and anions. Notice that oppositely charged particles are adjacent to each other. If I smack it with an external force like a hammer and dislocate it, you will see that one plane of ions will shift down by 1 unit, and as a result, we will now have similarly charged particles adjacent to each other. Cations next to cations, anions next to anions. They repel, and what do you know? The crystal cracks. Okay? And you can see this quite easily. If you have any rock salt in your garage, go out and get a big piece of rock salt, hit it with a hammer, it will not flatten out, it will in fact shatter. And that's because of the ionic bonding. Now, how do we compare the relative strength of ionic bonding in different ionic compounds? For that, we're going to use a quantity called the lattice energy. Every ionic compound has a specific value of the lattice energy, and it is defined as the energy that is released when 1 mole of a solid ionic compound is formed from its constituent ions in the gas phase. So, for example, if I take 1 mole of sodium cations in the gas phase and 1 mole of chloride ions in the gas phase, and allow them to come together to form a very, very stable sodium chloride crystal lattice, 1 mole of salt, 787.5 kilojoules of energy will be released. Released because you're going from a high potential energy situation, the ions in the gas phase, to a very stable, low potential energy situation, the crystalline ionic compound. That releases 787.5 kilojoules of energy, and that is a measure of how strong the ionic bonding is in sodium chloride. Well, let's compare that to another compound, magnesium oxide. If I take 1 mole of magnesium 2+ cations in the gas phase and 1 mole of oxygen 2- anions in the gas phase to form 1 mole of solid magnesium oxide, I get out 3,760 kilojoules of energy. It has a much greater lattice energy, indicating a stronger ionic bonding. How can we rationalize that? Well, in magnesium oxide, the ions have +2 and -2 charges versus +1 and -1 charges in sodium chloride. That means stronger electrostatic attraction between the cations and anions, which corresponds to stronger ionic bonding, and that is reflected in a greater lattice energy. So now let's move on and talk about metallic bonding. In a solid metal, we have metal atoms packed close together in a crystal lattice, but it's very different from an ionic compound. Okay? It turns out that metals, as we probably understand, tend not to hold on to their valence electrons very tightly. We know this because we know metals lose their valence electrons to form cations, but in a pure metal, those valence electrons leave the valence shell and are free to float throughout the metallic crystal. And here is a diagram that shows that. The red circles with a plus sign in it represent the nuclei and core electrons of the metal atoms, which have lost their valence electrons and hence have a positive charge. The small blue circles represent the valence electrons, which have left the valence shell and are now free to flow throughout the metal crystal. Okay? Every textbook uses the same term to describe this. It's called the mobile sea of electrons model. Okay? So the metal atoms release their valence electrons into the mobile sea of electrons. The nuclei and core electrons, as indicated by the red circles with a plus sign in it, remain in place, while the delocalized valence electrons flow freely among them. And the metallic bonding is simply the electrostatic attraction among the nuclei and the delocalized electrons. Okay? So, how does this explain observed properties of metals? Well, it's actually very cool how it explains these properties. Okay? First of all, we know metals have good electrical conductivity. Okay? Electric current flows very easily through a metal. How do we explain that? Well, that's pretty straightforward. The electrons in the mobile sea are free to flow through the metal when you apply a voltage, and that free flow of electrons through the metal is the electric current. So for example, if I were to say place a positive charge at this end of the metal and a negative charge at this end of the metal, the freely flowing electrons would very easily be able to move away from the negative charge from which they're repelled towards the positive charge to which they're attracted. That flow of electrons through the metal is electrical current. What about malleability and ductility? Malleability means when I have a metal that is fairly close to its melting point, if I smack it really hard with a hammer, it doesn't shatter like an ionic compound does, but instead it flattens out into a nice thin sheet. Okay? Ductility means, again, when the metal is close to its melting point, I can draw it out into thin wires without it breaking. Well, that's because metallic bonding is pretty much the same in all directions. So we can easily deform the metal by shifting the nuclei without disrupting the metallic bonding because the electrons can simply flow wherever they want. The final property is luster or shininess. Metals are all shiny. Why is that? Well, we can explain that with the same model. When a photon strikes the metal surface, the electrons at the surface atom, which are only very loosely held, are promoted to higher energy levels. When those electrons drop back down, they re-emit that light, which we observe as the shiny surface of the metal. So when you look at a piece of metal and you see it shiny or lustrous, what you're seeing are electrons being promoted, dropping back down, and re-emitting photons. Finally, can we compare the relative strengths of metallic bonding in different metals? We can, and for that we're going to use a quantity called the heat of vaporization. The heat of vaporization is the energy that you have to put in order to completely evaporate 1 mole of a solid metal. It is possible to evaporate metals, and you can measure the amount of heat that takes, and that is a measure of the strength of the metallic bonding. Obviously, the stronger the attraction between the metal atoms, the more energy it's going to take to separate them, and the higher the heat of vaporization. So for example, if I have 1 mole of solid lithium and I want to turn it into 1 mole of lithium atoms in the gas phase, I have to put in 147 kilojoules of energy to overcome the metallic bonding. So that 147 kilojoules of energy is a direct measure of how strong the metallic bonding is in lithium. So let's look at some examples of other heats of vaporization. I'm not going to hold you accountable for any of these. I simply want to ask you, do you see any trends? So here are some metals in groups 1, 2, and 13. And I want you to pause the video and look and see if you see any period trends. So this is second period, third period, fourth period, fifth period. And what do you observe as you move across the period? Well, clearly you see that the heat of vaporization is increasing, which must mean that the metallic bonding is getting stronger. How can we explain why the metallic bonding is getting stronger? Well, obviously, as you move across a period from left to right, you are increasing the number of valence electrons, which means there are more electrons in that mobile sea of electrons, which means there's a stronger attraction between the electron C and the nuclei, which corresponds to stronger metallic bonding. So just as we use the lattice energy to compare the relative strengths of ionic bonding and ionic compounds, we're going to use the heat of vaporization to measure the relative strength of metallic bonding among different metals. That's all for ionic and metallic, and in our next video we'll talk about covalent bonding.